There we go. All right, so make sure to get to the Monday assignment at some point in the future. And as always, the recording of the notes that we go over today will be under the, we're going to be talking about chemical bonds and how atoms kind of stick themselves together. So it's going to be under the chemical bonding Zoom meeting recordings up there, because that's also what the notes are about today. But for anybody that's really paid attention to my screen here, you may have noticed something a little bit different than our normal mix of stuff. And that is because this week in IPC, we have our first exam. And it is going to be a midterm exam. Why did I just get, anyways. Hold on, it just told me somebody's trying to get in to the room, but I do not see them showing up yet. So hopefully they do soon. Maybe it's just an internet thing. So the first thing that we have going on today, or that we have excuse me, not the first thing. Major thing coming up this week is our midterm exam. That means that it's going to be a big series of questions covering everything that we've talked about so far this week, including some of the stuff that's coming up on Wednesday. So you notice that even though this exam is going to go live on September 23rd, which is a Wednesday, it is not due until Friday. So I'm giving you guys 3 whole days to work on this exam, not because it's a super crazy long exam, but because some of the stuff that we talk about on Wednesday will be on the exam. And so I want to make sure you have a chance to kind of digest all of that. The exam is a pretty similar setup to some of the exams that you may have been taking if we were taking this class in person. So we've got a mixture of some multiple choice questions, some fill in the blank questions, the heating curve diagram, that guy's coming back, some short answer questions where you have to write in your answers, some stuff with the atoms that we've been talking about. So a whole host of different questions. Like I said, it's not a super long exam. It's only 20 questions long, but it does cover a pretty wide range of topics, which is why I wanted to let you guys know about it a little bit ahead of time, especially since you guys were so awesome at being here on the Zoom call. Where am I going? I'm trying to go back to the IPC page, but the stupid screen sharing thing is in the way. Maybe if I don't touch my computer for a couple seconds. There we go, that up a little bit. So just like with all of our other stuff, you can do it on the Google Docs, or there's a Google Form version that's set up in sections. And so each section has it's the exact same order of questions as the Google Doc version. It's just set up a little bit differently, so it makes it easier to take through the Google Form version, and it splits it up into the different sections so that you're not scrolling through a giant list of questions every time you want to go back and forth through the exam. So, like I said, that is coming up on Wednesday is when that will be posted. So the 23rd, but it is not due until midnight on Friday. So like I said, you've got 3 whole days to work on it and make sure that, so you feel free to take your time, read through every question. Obviously, there's no way for me to really prevent you from going back and looking at the notes while you're going through the exam. So it is in effect an open note exam, right? If you want to have one of the notes from the past couple weeks open while you go through the exam, I'm not going to stop you. All right, so that is what is coming up on Friday. Or excuse me, I keep getting it mixed around because it says Friday. The midterm will open on Wednesday, but it will not be due until Friday. Right, so that was the main thing that I wanted to share with you guys regarding kind of the stuff that's coming up later on in the week. Again, some of the stuff on the exam, especially if you get like jump started on Wednesday and you start to go through it early, some of this stuff, especially on the end of the exam, may look a little bit strange and new, and that's because some of the material that we cover this coming Wednesday will be part of the exam as well. And so it won't be until Thursday or so that you'll be able to see the whole, all of the material that'll be covered on the exam. All right. All right, so back to the oh, there we go. No, hold on, let me bring those back up. Okay. All right, so if you just joined on, I won't go through the whole spiel again, but I was bringing people's attention to the fact that our first exam is going to be posting this week. It'll be posted on Wednesday, but you have until Friday, the 25th, in order to work on it and finish it. It's only 20 questions, but it covers everything that we've talked about in class so far, all the way back from the solids, liquids, and gases, and the properties and changes, all the way up to the chemical bonding and including the mixtures and compounds nodes that we're going to be going over later this week. So keep your eye out for that coming up in your feeds. But for now, we're going to jump into the real meat of the notes today, which has to do with chemical bonds. So this is how atoms essentially are able to stick themselves together. And so when we're talking about bonding, we're not talking about this bond. And we're not talking about this even better bond. We're talking about chemical bonds. So we've been going over these atoms and these electrons and their reactivity and how we can determine where those electrons go on their shells. And so today we're going to cover how the atoms stick to each other. How is it that they can combine with each other in order to form bigger and bigger and bigger structures? All right, so, oh man, that's way up there. Oh, here we go. There we go. All right, so atoms are the smallest unit of matter, right? We can't get, they're made up of these little particles, but in terms of the building blocks of matter, we can't really break them off into any smaller pieces, right? Our protons, our positive protons, our neutral neutrons, and our negative electrons, they can't just be out living on their own, right? They have to be combined into these atoms. And so last week we were talking about these electrons and how they float around on their shells. So we discussed how you can figure out how many electrons an atom has by looking at its atomic number. And based on the couple homework assignments that you guys did with the electrons last week, a lot of you got this down pretty well. So the atomic number that shows up on its little periodic table box, that'll tell you how many electrons that you got in the atom. So we discussed how, whoop, that's not what I meant to do. We discussed how the electrons don't just randomly swirl around the outside of the atom, right? Instead, they occur at these specific electron shells. So the first shell can fit 2 of those electrons, the second shell can fit up to 8, and the third shell can fit up to 8. And so that kind of determines where these groups of electrons go around the atom. Are they on the very, very inside shell, or are they a little bit further out, or are they even further out? So the reason why we spent a lot of time going over those electron shells and figuring out which electrons go where is because we were trying to determine how an atom behaves, or we were trying to figure out something that is important. And that is that however many electrons we have on the outside of an atom can tell us about how it's going to react when it encounters other atoms. So these atoms are flying around in whatever solution or gas that they're in, and they come into contact with each other, and the electrons that they have can determine what sorts of interactions these atoms will have with one another. So we figure out the number of electrons, we can figure out where they go on their shells. And today we're going to learn about how we use those shells and those numbers to figure out how an atom reacts with other atoms. All right, so just a little bit of a review. We've got our first electron shell. That guy can hold 2 electrons, right? So pretty limited right there. And then the second and third shells can hold up to 8. So we're only going to worry about shells 1, 2, and 3. And so the maximum electrons that can fit on each shell are 2, 8, and 8. So the electrons that are on that outermost shell, whether the outermost shell is the first shell, if we're talking about really, really tiny atoms like hydrogen and helium, or if it's the second shell, like things like carbon and oxygen only go up to 2 shells, or if it's the third shell, things like aluminum and argon, whatever electrons are on the outside shell, those guys are called valence electrons. So they get their own special name for reasons that we'll talk about in just a second. So the valence electrons are the outside-most electrons, the ones that are on whatever the outside electron shell is around our atom. So here we have some basic diagrams. We have hydrogen that has the 1 proton and 1 electron. And so on this diagram, it shows little blank spaces wherever there could be an electron, but it's not filled in. So hydrogen only has the one electron. So even though he could fit 2 on this outer shell, he's only got 1. So he's going to be stuck there. Carbon has 6 electrons. And so he fills up his first shell with 2. But then carbon only has 4 electrons on the second shell. So there are 4 kind of blank spaces, right? There could be 8 electrons on the second shell, but carbon only has 4 electrons. And so he's got 4 on that second shell with 4 spaces where those other 4 could be if he had even more. And then nitrogen, 1 more electron than carbon. So he's able to fit 5 electrons on his second shell, right? 2, 3, 4, 5, plus the 2 on the first shell makes 7. But then he has 3 spaces where electrons could be. So he's only got 5 out of the 8 on the second shell, leaving 3 blank spaces essentially. And then similar with oxygen, he has 8 on that second shell, or excuse me, 6. We've got 2 on the first shell, 6 on the second shell. So there are 2 blank spaces. This is important because of something called the octet rule, which is going to play a big role when we talk about the chemical bonds in a second. So atoms really would like to have 8 electrons on their outer shell, right? Whether that's the second shell or the third shell, they really want to get that number up to 8. So if they are low on electrons in that second shell, if they only have 4 that can go on that second, like carbon can, that means they'd like to pair up with other atoms so that in the case of carbon, we could get 4 more electrons out there, right? So in order to get a full outer shell, carbon would like to gain 4 electrons. Nitrogen, to get his outer shell full, would like to gain 3 electrons. And then finally, oxygen, to get his outer shell full, would like to gain 2 electrons. So in order to get those 8 electrons on their outer shell, these are how these particular atoms would tend to interact with other elements. Carbon would like to make arrangements with other elements so that it can fill up its second shell with 4 more electrons so that it can have a total of 8. And then nitrogen wants 3 more electrons to have a total of 8. And oxygen wants 2 more electrons to have a total of 8. So if you remember from last slide, we were talking about the valence bonds. Carbon has the 4 valence electrons, 4 on the outer shell. Nitrogen's got 5 valence electrons, and oxygen has 6. However many of those outside electrons there are that are filling up those spaces means that our atoms need fewer and fewer electrons in order to get that full 8. All right, so oxygen has an atomic number of 8, 2 on the first shell, and 6 on the second. And so because oxygen has 6 valence electrons, 6 outside electrons, he wants to react with other elements so that he can get those 2 more electrons to get his total up to 8. All right, let me write down some people that just joined. Okay. So here we have some more diagrams of different atoms, just showing how many electrons go on each one of their shells. Right, so we were just talking about carbon, nitrogen, and oxygen. You see fluorine over here just past oxygen, number 9. So he has 9 electrons, which means that he's got 2 on the first shell and 7 on the second shell. So fluorine only needs 1 more electron in order to get that full outer ring. Neon, on the other hand, over here, has 2 first shell and 8 second shell electrons to give us a total of 10. So neon does not want any more or any less electrons. Neon is super happy with all of his outer shell being full. Same thing with argon down here. Argon has a full third shell of electrons. So 2 on the second, 8 on the 2 on the first, 8 on the second, and 8 on the third. So argon also does not want to interact with any other elements. He is happy just the way he is. But you'll notice that a lot of these atoms underneath the ones we were just talking about have the same set of valence electrons, the same set of outer electrons. Melissa is asking about, does it matter where you put the first 2 electrons? And the answer, Melissa, is yes. The first 2 electrons will always go on that first shell. So like if you see up here, we have hydrogen and helium, first 2 elements on the table.
Well, I'm sorry, I didn't mean that. I know it goes on the first shelf, but I'm saying, does it matter like where on the first shelf does it go?
No.
Okay.
Okay, gotcha. I see what you're saying. So yeah, it doesn't really matter where you put them in terms of like the little pictures that were drawn over here. Like if you put 2 dots over here or 2 on the bottom or 1 on each side, that doesn't matter because it's just sort of an illustration of where the electrons are at. In reality, the electrons are never sitting still. They're always moving. They're in constant motion around the atom. But obviously we can't have there be constant motion in a picture because that's not how pictures work. And so whenever we're showing how many electrons are on a specific shell, we just put them, you can put them wherever you want on the shell, to be honest, just as long as the number is correct. All right, good question, good point. So the third shell has a lot of similar characteristics as the second row here, right? So oxygen had 6 electrons on its outer ring. Sulfur also has 6 electrons on its outer ring. The only difference is that oxygen has the electrons, its outer ring is the second ring. Sulfur has some more electrons. He filled up his second ring. And so sulfur has 6 electrons on the third ring. Same thing with carbon over here. Carbon has 4 electrons on his outer second ring. Silicon has also 4 outer electrons, but they are on the third ring, the third shell right here. So similar setups in terms of their outer electrons. They're just changing up which shell that they're on. So remember, I mentioned earlier that the valence electrons, the outside electrons, are the ones that are going to be really important for today. And so that's why I'm focusing on the fact that like beryllium has 2 outer electrons and boron has 3 outer electrons. Magnesium also has 2 outer electrons, and aluminum has 3 outer electrons. And so earlier when we were talking about that octet rule and how atoms really want there to be a full outer set of electrons, the way that they do that is by either giving away or sharing the electrons on their outermost ring, those valence electrons. So it doesn't really matter how many total electrons an atom has. What's most important when it comes to these chemical bonds is how many are on that outside ring, whether it's the second ring or the third ring. However many electrons are on it, that'll tell us about the ability of that atom to gain or lose a certain amount of electrons with other atoms. So another way, if you didn't want to show all of those extra rings and stuff, another way to show how many electrons are on the outer shell of an atom is through something called electron dot structures. I'm mostly showing these to you guys right now, just so that you can see what they look like. They might come up, I think, a little bit later on in the notes, but you're not gonna have to go in and draw these out for a homework or something in the future. But I just wanted to show you that if you see a structure that looks like this, what exactly is going on. And so again, earlier we were talking about how carbon has 4 electrons on its outer ring. And so there are 4 little dots that go around carbon. And then same thing with the next row down with silicon. Silicon also has 4 electrons on its outer ring. So there are 4 little dots around silicon. Fluorine has 7 electrons on its outer second ring. So there are these 7 dots around this F for fluorine. Chlorine is similar. It has 7 electrons on its outer third ring. So there are 7 of these little dots around chlorine. So if you ever see these kind of pictures in the future, just know that they're showing how many of those valence electrons, how many of those outside electrons are on a particular atom. All right, if we go over here, things like lithium and sodium both only have 1 outer electron, and things like beryllium and magnesium only have 2 outer electrons. All right. I'll go ahead and pause it right there for a second. Any questions so far about our electrons, the rings, or what's going on with these outside electrons? Any questions, any uncertainty about any of that so far? All right. Not hearing anything from anybody, which I'm forced to assume means that everybody has this down perfectly hunky-dory so far. So it seems like I've been focusing a whole lot on these outside electrons, right? And so
Excuse me, I have a question. Can you hear me?
yeah, hi Lily, go for it.
Okay. So I kind of missed some of the first part, and
Sure.
I was wondering, where do I go to see the video or the notes? I know where the notes are, but it doesn't show when you're recording it and it's explaining it. So I kind of like, it takes me a long time to understand what it's going with. So
no worries. So if you ever want to go back and watch the video of me going through it, as soon as we are done today, all of the videos for all of the past notes go in this Zoom meeting recordings section on our Google Classroom. So if you go to the classroom, click on the classwork page up at the top, and it'll bring up a list that looks sort of like this. Scroll down a little bit, and Zoom meeting recordings is where it'll be at. So each one of these tabs has a link to a video of me going through the notes. And so once the video for today is done and processed and uploaded, it'll go here in the chemical bonding section. And then if you ever want to read through the notes again, they'll be down here in the 921 Monday notes section down under week 4.
Okay, so I go to classrooms and then I hit
This is just
where it says the notes, you said?
because it's a new phone, it's new.
So classwork or classroom, and then classwork up at the top, or depending on some phones, it might show up on the bottom.
It'll back up your stuff for you.
And then the Zoom meeting recordings is where.
So here,
So, but it's not on the one that says the notes.
so right here.
I'm trying to
where it
see
says
where you're
play, where it
at.
has the little triangle,
Because
Exactly.
when I see, I always look for the notes.
you can go to
And
apps like
I'm
Pandora.
going through and reading, but then,
Snapchat,
you know, I
Facebook,
kind of
stuff
don't
like that.
understand. So
You don't
then I
have to
just
get it,
kind of
but
takes
you
me a
can
little
get those
longer to
apps.
figure it out, like I did the other one.
Mhm. Sure.
Mhm.
So yes, it's the video and the notes are not like together in the same.
Yeah, okay, yeah, see, so that's what I was a little confused on. Where do I find the
It's up
video?
to you. I think Pandora's good.
So
because
all of the videos are going to be
not just
under the Zoom meeting recordings.
to download an app.
So
this
do
is
I
where
click on the Zoom recording or no?
Typed in Pandora, it popped up.
Can you tell me one more time? So I go on to the Zoom where the Zoom meetings are at.
And
So no, when you want to watch the video again, like if
Uh-huh,
tomorrow you
Uh-huh.
want to watch me go through these notes again,
uh-huh,
you'll go on to Google Classroom.
uh-huh.
You'll go under the classwork section, like where the notes are, and then the videos are
Everything I
posted
really need is like
under
Under
the
Zoom
Zoom
recording.
meeting.
Oh, okay, okay. Oh, okay, got it.
maps.
it's down there at the bottom.
All
So like
right.
here's our
Have a map.
video from the first week of class, and
Uh-huh.
then our two videos from the second week of class,
Mhm.
and then the video
Well,
for
now
today
it's already logged in.
will be
Yeah.
posted right here once we're done with class.
It signs
Oh,
in
okay,
all
got
the
it. Thank you.
stuff. So right now, see,
You are welcome. All right. So some other questions that are coming in are about, I've talked about the electrons want to have their shells be full of valence electrons. What we haven't gotten to yet is how do they do that? How do they get there? Whoops, that's not where I wanted to go to. There we go. All right, so that is what we're going to be doing next. The way that electrons are able to fill up those outer shells by borrowing or sharing between different atoms is through what are called chemical bonds. So chemical bonds are how our atoms are able to either gain electrons in order to fill up their shell, or if they are atoms like lithium and sodium, or beryllium and magnesium, these guys maybe want to lose one or two atoms, or electrons, excuse me, in order to have a full second shell. So we're going to go through 3 different ways that atoms can bond together and share or donate their electrons in order to get their full shells. The 2 that we're really going to focus mostly on are called ionic bonds, where we transfer an electron from one atom to another, and covalent bonds, where two atoms share an electron between them. We're also going to talk a little bit about metallic bonds, which has to do with how metals are able to bond with one another and form those superconductive areas. But we're not going to focus on those ones as much because it's not as kind of important as these first two, ionic and covalent bonds. So we're going to go through these one by one and kind of talk about what's happening with each one. So like I said, the first one that we're going to cover, ionic bonds, are when two atoms get bonded together by transferring an electron from one atom to the other. Essentially, there's one atom that has a very empty outer shell. He wants to give away his electron to an atom that has a very full outer shell, so that the first atom can then have a, if it had a very empty third shell, maybe it gives that shell electron away, and so now it has a full, happy second shell. Vice versa, if there's an atom that had a mostly full third shell and really just needed one more electron to fit, it could transfer that electron from that first atom, take it in, and now it has a nice full third shell. It's kind of hard to talk about in words, but we'll go through some pictures that'll hopefully kind of show off what's going on. So some general kind of characteristics of ionic bonds is they tend to happen between metals and non-metals. So metals, things like sodium, potassium, aluminum, iron, gold, silver, tin, and non-metals, things like carbon, oxygen, phosphorus, iodine, sulfur, stuff like that. We haven't really talked about electronegativity in this class, so don't worry about that one too much. Just know that it tends to be metals and non-metals together. And again, we're transferring electrons from one atom to another. We're essentially giving away an electron from one atom's outer shell to another atom's outer shell. So when you get these electrons transferring from one area to another, you tend to have charged atoms, which means that the charges on an atom are no longer balanced, right? Because before we had equal numbers of protons and electrons, and that's how I figured out our electron number. But now we're giving away electrons, which makes us more positive, or we're taking in electrons, which makes us more negative. And so ions is just a fancy word for atoms that have positive or negative charges on them. And so you don't have to worry about knowing like how positive or how negative that it is. Just know that with an ionic bond, you tend to create a more positive atom and a more negative atom. And we'll look at what that looks like in just a second. So things like sodium chloride, aka table salt, where we have a metal and a non-metal together. We can also have calcium dichloride, where we have two non-metals and metal. And then potassium oxide, so K is the symbol for potassium, which is a metal. And again, oxygen is a non-metal. So what does it actually look like when we take electrons from one area to another? So it looks something sort of like this. So we have our, if there's any way to pause this, I promise I would, but it's just kind of keep going. So we have our sodium over here, right? We just talked about how NaCl is a good example of an atomic ionic bond. And if you remember from way earlier, Sodium just has the one electron on its third shell. Chlorine, on the other hand, has 7 electrons on its third shell. So chlorine's only missing 1 electron to have a complete shell. If sodium is able to give away this one third shell electron, then it could have a full second shell. And as we know from the octet rule that we were talking about earlier, whatever the outer shell is, atoms want it to have 8 electrons. So sodium is trying to give away an electron to have a full second shell. And chlorine is trying to accept an electron to have a full third shell. And that is what's going on in here. So the red dots are all of the original chlorine electrons on that outer third shell. And then the yellow dot is the single electron that was on the outer third shell of the sodium. So when they make an ionic bond, sodium gives its electron to chlorine. Now, when they do this, the reason that it's called is because sodium and chlorine then just don't go their separate ways and have happy, full lives away from each other. Instead, sodium is giving away its electron, which makes it a little bit more positive, right? We talked about how electrons are negatively charged, so they got a negative charge. So when sodium gives away that negative charge, chlorine becomes a little bit more negative, and sodium becomes a little bit more positive. So because one is positive and one is negative, if you've ever heard the term opposites attract, well, when it comes to science and chemistry, that is extremely true. Positive atoms and negative atoms are, because of that change in their charge, they tend to be attracted to one another. Positives and negatives like to stick together. And so that's why these guys get bonded when sodium gives away his electron to chlorine. The sodium becomes a little bit more positive, the chlorine becomes a little bit more negative, and the opposites attract, sticking the sodium and the chlorine together. One way to kind of think about it, if you want to think about it this way, is that imagine the two atoms as like two dogs, where one dog, in this case the sodium dog, is like a little dog with a bone, and chlorine is like a big dog with a bone. Chlorine will take away the bone from the sodium. In this case, that's an electron. So chlorine's got a whole bunch of electrons, but he really wants that one more to have the full set of 8. So chlorine will take the electron from sodium, and then sodium will still stick nearby. In this case, it's kind of thinking of it like the little dog is still hoping to get the bone back. But in reality, it's that the positives and the negatives attract each other. So this is what's going on with ionic bonds. One element is giving away a couple, 1 or 2 electrons. Another atom is accepting those 2 electrons. They both get what they want. They both have a full outer shell. But because of the positive and negative charges that go on, they get attracted to each other. And that's what creates that bond. All right, any questions about the ionic bonds so far?
I have a question.
Yeah, go for it.
So I'm trying to figure out if the chlorine in this case has like the electrons or whatever or atom, whatever it's called, if
Mhm.
they, it's hard to, I'm trying to explain it in a way that you can understand. So the sodium has the one and it's given the one that it has so that the chlorine can have a full outer shell, then that means that the sodium doesn't have any electron, whatever. And so then what happens with that though?
Great point. So I forgot that this picture was in here and might help you a little bit with that. So when the sodium gives away that electron, you're right, it doesn't have a third shell anymore. All of its third shell electrons, it just had the one, and now that's gone.
Mm-hmm.
So instead, the outer shell of sodium becomes the second shell. So sodium doesn't only have the one electron, right? The atomic number of sodium is 11. So it has 2 on the first shell and 10 on the second shell. It has 1 on the third shell. Or 2 on the first shell, 8 on the second shell. Excuse me, getting ahead of myself. So it's got 10 on the first and second shell, and then just the 1 on the third shell.
Mm-hmm.
The sodium gives away that electron. It doesn't have a third, it's got 0 on the third shell now. So instead, its outer shell is the second shell.
Okay.
All right. And so you're right that its third shell, it doesn't have one anymore. And so because it doesn't have one, that isn't considered the outer shell anymore. Now, the second shell is the outer shell because that is the biggest shell that still has electrons on it.
Okay. Okay, that makes sense.
Carmen had an earlier question about the conductors and high melting points. Carmen, don't worry about that. I took this presentation from a different teacher who hit on some of the different points a little bit differently. So don't worry about that part about the conductors and the high melting point from these notes earlier. Mainly just focus on its metals and nonmetals sticking together by transferring their electrons. So we're moving from one atom to another atom. So again, just to kind of walk through it, sodium has 11 total electrons, 10 on the first 2 shells, and then 1 on his outer third shell. Chlorine has 17 total electrons, 10 on the first 2 shells, and 7 on the outer shell. So when they make an ionic bond with each other, sodium gives the electron to chlorine. So now, sodium's outer shell is the second shell, which has 8, so sodium's happy. Chlorine's outer shell is the third shell, which also has 8, so chlorine's happy. Since sodium gave away that negative electron, sodium becomes a little bit positive. Since chlorine accepted that negative electron, chlorine becomes a little bit negative. And so the positives and the negatives are attracted to one another, and that's what sticks the sodium and chlorine together. That's what bonds them to each other, is this attraction between the positive and negative atoms. All right, good questions so far. Any more ionic bond related questions? All right, so our next one is a little bit less tricky. I think there's one more picture. So when we get a whole ton of sodium and chlorine together, it makes sodium chloride, which tends to form in these big blocky crystals, which we normally refer to as salt. So the salt that we put on our food and that we eat, normal table salt, is sodium chloride. That's its atomic structure. So it's just a whole bunch of these sodiums and chlorides that have bonded to one another that then form up and make these really big crystal shapes. All right. So covalent bonds are similar to ionic bonds in that they both cause atoms to kind of stick together. But in covalent bonds, we don't give away electrons from one atom to another. Instead, the electrons get shared. So both atoms essentially kind of take hold of a single electrons, or in some cases, they share multiple electrons between two atoms. So if ionic bonds were all about kind of give and take, covalent bonds are all about sharing. So covalent bonds tend to happen between non-metals, non-metallic elements. And it's all about sharing electrons with each other. Again, don't worry about the stuff about ionizing conductors, blah, blah, blah. But so you've probably heard of a lot of atoms that make covalent bonds. Things like water, H2O, is two hydrogen atoms covalently bonded to an oxygen atom. Carbon dioxide, so the stuff that comes out of our power plants and comes out of your car, is two oxygen atoms covalently bonded to one carbon atom. And then sometimes atoms will form covalent bonds with their twins, essentially. So oxygen, two oxygen atoms tend to form covalent bonds with each other so that they can both get a nice full outer shell. So covalent bonding is a little more straightforward than ionic bonding because there's not all this giving away and taking up and then the plus and minus coming together. Instead, the atoms literally just share their outer shell electrons. So here is a pretty basic atom. We've got CH4, one carbon and 4 hydrogens. So if you remember, carbon has 6 electrons, 2 inner shell electrons, which are not pictured here, and then 4 outer shell electrons. So in this case, the little blue dots around here are our carbon electrons. So we have 1, 2, 3, 4 valence electrons for carbon. Hydrogen, our super duper simple atom, has 1 outer shell electron. So carbon really wants to have 4 more electrons bonded to it, right? We talked about that octet rule where they want to have the 8 outer shell electrons. Carbon only has these 4 outer shell electrons, so he really wants 4 more in order to get that full set. Hydrogen has just the 1 electron on his first shell, so in order for hydrogen to have a full outer shell, he just needs 2 electrons. And then his outer shell, which for hydrogen happens to be the first shell, will be nice and full. So what do? The carbon and the hydrogens share their electrons with each other. In this case, since carbon can make 4 connections because he needs 4 more electrons, he'll connect to 1, 2, 3, and 4 hydrogen atoms, so that now with the 4 carbon atoms or electrons and the 4 hydrogen electrons, we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons on the outer ring of carbon. So carbon is a happy atom. All these hydrogens similarly have 1 hydrogen and 1 carbon electron that they're sharing with each other. So this hydrogen has 2 outer shell electrons on his first shell, so he's happy. This hydrogen has 2 outer shell electrons on his first shell, so he's happy. This hydrogen has 2 outer shell electrons on his first shell, so he's happy. And number 4 hydrogen down here has 2 outer shell electrons on his first shell, so he is happy. Each one of these atoms gets what they want. Carbon, by bonding to 4 hydrogens, gets 4 extra electrons on his outer shell to get 8. And each one of these hydrogens shares one of these electrons with carbon, so they each get 2 on their outer first shell, which makes the hydrogens happy. So when it is in motion, it might look something kind of like this. Here we have 2 kind of unspecified atoms. Which ones they are aren't super important. But you'll notice that each one has 7 outer electrons. So maybe this is something like fluorine. Fluorine has 2 first shell and 7 second shell electrons. So when 2 fluorine atoms come into contact with each other, they're going to be very likely to each share their 1 single outer shell electron, so that by sharing with each other, they can both feel like they have 8 electrons in their outer shell, right? Fluorine 1 has his 7 original electrons plus that 1 from fluorine 2. And fluorine 2 has his 7 original electrons plus that 1 he's sharing with fluorine number 1. All right. Hopefully a little bit more straightforward than the ionic bonding, but any questions about covalent bonds so far? Let's see here. All right, looks like nothing's coming up in chat either. All right. So
We can always go back to the
bonds
notes.
all about
right?
sharing. They're not giving away or taking in any electrons from each other. Instead, they're sharing those outer electrons so that each atom feels like it has a full outer ring. So those were the main 2 that I wanted to make sure to kind of really hit with you guys today, is the ionic bonds and the covalent bonds. There is one more type of bonding that isn't as important, so I was just going to go over it pretty quickly. Metallic bonds. So when we have, if you remember, ionic bonds tend to be metals and nonmetals together. Covalent bonds tend to be 2 nonmetals together. And so metallic bonds are our final group when we have 2 metals together. So instead of the electrons being shared between one atom and another, or being donated from one to the other, instead, metals tend to form what are called these electron clouds. So the electrons are kind of all shared equally between all the different atoms of a single metal. So like when we have a big aluminum foil sheet, one of the reasons why these metals tend to have the characteristics that we talked about last week, they're shiny, they're bendable, they're good conductors. That's due to the fact that when we have a lot of the same atom of a metal all combined together, they tend to form these big clouds of kind of evenly spaced electrons. So it's sort of like this, where we have to use those dog examples from earlier. Instead, we have lots of dogs that are kind of being surrounded at all times by lots and lots of bones. So this is kind of sort of what it looks like on a atomic level. It's like all these electrons are all being kind of equally dispersed and spread around all the different atoms of the metal. So it's almost like a sea of these electrons all over the place. So like I said, that is sort of what metals do, but the ones that I really wanted to focus on were those ionic bonds with the transferring electrons between each atom and the covalent bonds. Where atoms share the electrons that are in between them. All right, so there's not going to be any questions on the exam coming up or on the homework about metallic bonds. I just wanted to mention it because those are out there as well. But the main things to focus on are our ionic bonds and covalent bonds. Either metals and nonmetals transferring electrons from one to another, and then the positives and the negatives becoming attracted, or atoms sharing those outer ring electrons with each other. And again, they're all doing this because they're trying to get to that 8 electron outer shell. They're all trying to follow that octet rule. So whether or not they have to give away or accept electrons, or whether or not they have to share electrons between atoms, it's all trying to get to that outer 8 on the outer shell. Except for hydrogen, he just wants 1 more. But everybody else wants to get up to 8. All right, and I think that brings us to the end of the notes for tonight. All right. Any final questions about our different types of bonds? The ionic bonds, the covalent bonds, those valence outer shell electrons, the octet rule. Any questions about any of that stuff that we've been going over so far? Right, awesome. So again, just to kind of give you guys a preview for what's coming up this week. Nope, not that one. There we go. So tomorrow's daily assignment has to do with the chemical bonding that we've just been talking about. And it's a super duper simple one because I wanted to make sure that you guys got like the basic concepts of the different types of bonding. And so there's 2 diagrams of some different atoms. And so for each diagram, I want you to tell me what type of bond is being pictured in the image, and then a short 1 to 2 sentences on how can you tell? What is telling you or what suggests to you that this guy is a covalent bond or an ionic bond? So how can you tell what type of bonding is going on in this picture and what type of bonding is going on in this picture? Oop, I just realized that there's something wrong in picture number 2. If you can tell me what's wrong in picture number 2, bonus points for you. But the same concept is still the same. So for each one of these images, letting me know what type of bonding is pictured and what tells you that it's specifically that type of bond. What are the clues that are kind of cluing you in there? So that is the assignment that I'll be posting, let's see, about 6-ish hours from now, due on Tuesday. Again, coming up this week, our first exam, our first online exam, which once again will be posted on Wednesday, the 23rd, but it is not due until Friday. So feel free to take your time, go work on it, come back a little bit later if you need to, especially also because some of the stuff that we talk about on Wednesday will be covered on the exam. So that is coming up later this week as well. So make sure you keep your eye out for that. And finally, as always, the notes that I just went over about all the different types of bonds are on our 9/21 Monday notes, chemical bonding, on the Google Classroom. And once this video is finished processing and uploading, it'll go right here in our Zoom meeting recordings for 9/21 on chemical bonding. All righty, let's see. Wait a second. Have you guys seen anything that I've been talking about for like the last couple minutes? Oh, wait, no. Okay, there. For a second, I thought I wasn't screen sharing, and I was like, oh my gosh, I've just been talking to myself for the past 5 minutes. But I am, and you guys saw it. Whew. Scared myself there for a second. Okay. Any final questions about stuff going on in IPC class for week 4?
Now, Mr. Stanley, like for advisory, can we work on the homework? Or, I mean, like for IPC, can we just say that for tomorrow? Or,
Yeah, sure.
okay.
Still, if you want to like come in and check in, I think we might have a presentation going on for people who are coming to advisory tomorrow about some certification type stuff that Jeremy and Carolyn are going to come back and talk some more about.
Oh, okay.
So I'm not going to go the whole time, and if afterwards you have like some questions that you want to ask me about or anything like that, then I'll be more than happy to help answer them.
Because you said we have an exam, right? And then we do on what, Friday? Okay. And it's just going to cover everything we've already been talking about.
Yep.
Right? Okay. All right.
Yeah, everything going back to the solids, liquids, and gases, and the properties and changes, as well as the stuff about the atoms and their structure with the protons and the neutrons and stuff like that. All of it will be on the exam.
All right. Thank you.
No problem.